So we just did an introduction into galvanic cells, which are also known as batteries. So batteries are technically two half cells, and they are separated by a salt bridge to complete the circuit. And I'm sure you looked at a commercial battery before, and you see that they have a positive terminal and a negative terminal. And so that is really telling you what side is the anode and what side is the cathode. So the negative end of a battery, that would represent our anode, and the positive end represents our cathode. The cathode end is the side where reduction is occurring, and the anode end is the side where oxidation is occurring. So anytime you see galvanic cell or voltaic cell, just think of batteries. Now let's practice drawing a galvanic cell, putting together all of the terminology and oxidation reduction, anode cathode, electron flow, sign labeling, basically everything we've talked about so far. So the reaction that we were given is copper plus 2 silver ions forming copper 2 plus and 2 solid silver. So that's our balanced redox reaction. We're going to want to be able to break that up into two halves, one for oxidation, one for reduction. And to start by drawing, we're going to have two separate half cells. So we're going to have two beakers that are going to have two electrodes that are dipped in them. So those are our metal strips, our metal electrodes. And those electrodes are going to have to be connected by a wire. And imagine on top of our wire we have a little light bulb. And if our circuit is working correctly, our light bulb should be able to turn on. It's not on yet because we haven't done any of our redox reaction yet. Our electrodes have to be dipped in a solution. So we're going to have some solution in both sides. And next we have to complete the circuit by connecting them with a salt bridge. So this U-shaped glass is what our salt bridge is. And we can fill our salt bridge with something like potassium chloride, which is potassium ions and chloride anions, which will allow us to complete the circuit and remain electrically neutral on both sides of our half cells. So looking at our overall reaction, we can see that copper went from a 0 oxidation state on the reactant side to a +2 oxidation state on the product side. So in order for it to go from 0 to +2, the copper must have been oxidized. So that's going to represent our oxidation half reaction. And I'm going to put that on the right-hand side. So our oxidation half reaction is solid copper losing 2 electrons to become copper 2 plus, which is aqueous and in solution, plus those 2 electrons, which are on the product side because we have an oxidation that occurred. So this electrode would represent our solid copper in this case. And the solution that could be in here could be something like copper nitrate. The nitrate would just be a spectator ion. So in our solution, we have aqueous copper ions flowing around, and we have some nitrate ions also flowing around in there. Now on the other side, we had silver, which was a +1 oxidation state, and that became solid silver, so 0 oxidation state. So silver must be being reduced. And I'm going to draw that on the left side of our half cell. So this electrode would be solid silver, and our reduction half reaction would be Ag+, so silver plus. And we have 2 of them, notice, in our reaction, so we can put 2 there. And each one would gain an electron, so +2 electrons total. And that would give us 2 Ag, which is just 2 silver, so solid silver there. And don't worry too much about the balancing right now. We'll talk about that a little bit later. So in on the left-hand side here, this is where we have our reduction taking place. So based upon where I drew my oxidation and reduction, it didn't really matter what side I put them on, but now we need to be able to label our cathode and our anode. Since the reduction is on the left-hand side, this is going to represent our cathode. And so that means that a partial positive would develop on our cathode. On the right-hand side where we have oxidation, oxidation occurs at the anode. And so the charge on that electrode is we would end up having a partial negative on that electrode for our copper electrode. And now thinking about how our ions are going to flow and how our electrons are going to flow. That's kind of the next important part of this. So we said electrons always flow from the anode to the cathode. So notice I swapped what side I made the anode and the cathode on in this example compared to the one we looked at in the previous lecture, just so you could see that it doesn't matter what side they're on, you still have to follow the general principles. So on the right hand side we have our anode. This is the half reaction where electrons are being produced. So the electrons are going to start here and they're going to flow from the anode to the cathode. So from right to left in this sketch is the direction of the electron flow. And in terms of ions, anions migrate towards the anode, cations migrate towards the cathode. So actually we had to draw in our solution for our silver side. Our solution could be something like silver nitrate, AgNO3. There would be silver ions swimming around in there, and then spectator nitrate ions that are not participating. And in our salt bridge, let's place some potassium chloride in there to maintain electrical neutrality. And so showing now the migration of our ions is also important. So on the left-hand side, we have our cathode. So cations are going to flow there. So positive silver cations will flow towards the cathode, and they will be reduced to elemental silver. So that side will gain mass. Also, potassium ions, those are cations, those are going to flow from the salt bridge towards the cathode as well. On the right-hand side, at our anode where oxidation is occurring, that's where our anions are going to flow. So in this case, we're going to have nitrate ions that are flowing there. We're also going to have negative chloride anions that are in the salt bridge flowing in that direction as well. And so at that electrode, that's where solid copper is being oxidized to copper 2+. So technically this electrode is going to end up getting smaller and losing mass because the solid copper is going to end up breaking off per se and becoming copper 2+ ions that will be swimming around in solution. So some of that copper is going to leave and enter into our beaker over here. So when you're practicing drawing a battery, you want to be able to identify which reaction is your oxidation, which one is your reduction, and then thinking about reduction always happening at the cathode, oxidation always happening at the anode. The cathode develops that positive sign, the anode develops that negative sign, and we'll kind of look at why a little bit closer on the next slide. In terms of electron flow, electrons are the product of our oxidation reaction, and so they're flowing from the anode to the cathode where they're being consumed as a reactant in the reduction half reaction. In terms of the ions, you can remember that anions migrate towards the anode, so negative charges, and cations migrate towards the cathode. So those are kind of all the important things and terminology that you really want to get down pat when understanding galvanic cells. Okay, so now let's look at a little bit of a close-up of where the sign on each of those half cells even comes from. Where does that positive sign at the cathode come from? Where does the negative sign at the anode come from? And by looking really closely at these ions in solution, looking at our electrodes, we can kind of see why each side does develop a slight positive and a slight negative sign. So this is actually a really close, zoomed in, much nicer picture than the one I could just draw on the previous slide of our silver and copper redox reaction that we drew. So on the left, we had our cathode, and that was where we had our silver. We had silver ions gaining electrons to become elemental silver at our cathode. That's where reduction took place. Recall reduction is where we have a gain in electrons. And on the right-hand side, at our anode, where oxidation was taking place, we had our solid copper, and that was losing electrons to become aqueous copper 2+ ions. And so in that case, our electrons were a product of our oxidation half reaction at the anode. And so now looking really closely into this picture right here, we can see what's taking place at our silver surface on the cathode. The cathode is where reduction is happening, so electrons are being gained by those silver ions in solution in order for elemental solid silver to plate out. So when the metal ion actually collides with those electrons, it'll gain electrons, and it'll end up becoming reduced. So imagine that this yellow positive sphere is your positive silver ion, and it's coming in contact with an electron that's on the surface of the silver electrode. And so once those two come in contact with each other, that positive silver plus ion will become reduced to solid silver. And so that's why you end up gaining silver mass on that electrode at the cathode there. So here's another one. You have a silver ion, that yellow sphere, +1 charge. It comes in contact with an electron. Together they combine to form neutral solid silver. So it's reduced at that location. Now, those electrons that are on the surface of your cathode, they're being used up. They're getting used up. They're a reactant in that reaction. And so if they're being used up and going away, you're left with a partial positive charge at the cathode because you're using up those electrons. And so the exact opposite is happening at the anode. So where oxidation is occurring. So our oxidation reaction was copper becoming copper 2+, and in order for that to happen, it had to lose 2 electrons. So when we have some solid copper that's on our copper electrode, and essentially it becomes copper 2+, and it turns into an ion that's going to be swimming around in solution, in order for that to happen, it must have lost electrons. And those electrons that are lost are retained on the surface of that electrode. And so the electrode becomes partially negative charged because those electrons are building up on that surface. So the metal atom on the surface of the electrode loses those electrons, becomes oxidized, yes, so copper went from solid copper, became oxidized to copper 2+, but those electrons are a product of that oxidation half reaction. And so they are still hanging out on the surface of that electrode, which those electrons left behind is why the anode ends up having a slight negative charge. So these two redox reactions occurring in their own separate containers is where we get those partial positive and partial negative charges that you see on a battery when you pick up a commercial battery. All right, so let's try one more example where we do this really longhand notation of drawing out a full galvanic cell We're going to sketch the experimental setup. We want to identify on our drawing what side the anode and the cathode is. We're going to indicate the direction of the electron flow. We're going to indicate how the ions are flowing. We're going to label each electrode as either anode or cathode and also label the sign on each electrode. So our reaction we're given is a solid iron plus aqueous tin, so Sn2+ is tin ions, forming aqueous iron ions and solid tin. So to start by drawing, we're going to draw that kind of same generic setup here. We got two separate beakers, and we're going to place an electrode in each of them. It's our solid strip of metal. We're going to connect our electrodes by a wire, and you could have a voltmeter up here, you could have a light bulb, just something that we're going to show that we are turning chemical energy into electrical energy. Each of our electrodes are going to be dipped in a solution. And now it's up to us to make one side our anode and make one side our cathode. So first we want to identify who's being oxidized and who's being reduced. So looking at our overall reaction that was given to us, we have iron, which is at a 0 oxidation state, becoming iron 2+. So if iron is going from a 0 charge to a +2 charge, it must have lost 2 electrons. And if it lost electrons, remember that Leo, lose electrons, is oxidation. So I'm going to put that on the left-hand side this time. So oxidation reaction that's occurring is we have our half reaction is our iron is going to iron 2+, and it's losing 2 electrons. And so our electrons of our oxidation reaction are a product. And so since I wrote oxidation on the left-hand side, that means now I've defined what side is my anode. Oxidation always occurs at the anode. So now this side of my half cell has to be my anode because I wrote my oxidation reaction over there. Moving over to the right-hand side, this is going to have to be my reduction half reaction. So in this case, the reduction reaction is aqueous tin ions, and they're going to have to be gaining electrons and forming solid tin. And the cathode is always where reduction occurs. So now that we've kind of got the generic basics down, we've picked a side to be our anode, we've picked a side to be our cathode. We know that our cathode develops a positive charge on that terminal, and our anode develops a negative charge on that terminal. So we can throw our signs in there as well. And a little bit more labeling here just to make our picture a little bit clearer. Our electrode on this side, this is going to be our solid iron, and our electrode on the right side, that's going to be our solid tin. Our solution that our iron electrode could be in could be just something like iron nitrate, so FeNO3 That means we got iron 2+ ions swimming around and some nitrate ions as well. And our solution that our tin electrode could be dipped in could be something like tin nitrate. So tin 2+ ions swimming around and some nitrate ions. Lastly, we're going to connect the two half cells with a salt bridge. So that's our U-shaped salt bridge. And we're going to pack it with some potassium chloride. So K+ and Cl-. Next, we want to show our migration of our ions and the flow of our electrons to kind of finish off our galvanic cell. So our electrons, we said, are a product of our oxidation reaction. So electrons are being produced over here, and then they're being consumed by our reduction half reaction. So they're a reactant. So electrons will flow in a galvanic cell from the anode to the cathode. So we're going to show our flow of electrons by drawing some arrows pointing in this direction. Anions migrate towards the anode. Cations migrate towards the cathode. So on the left, we have our anode. So our anions are going to start migrating that way. That could mean our spectator nitrate ions are migrating in that direction. The negative chloride ions that are in the salt bridge are also migrating towards the surface of that anode. On the right-hand side, our cations are heading towards the cathode, the electrode. So tin 2 plus ions are heading towards the tin electrode, as well as positive potassium ions are flowing out of that salt bridge and into the solution and heading towards that cathode as well. Only the tin 2 plus ions are actually being reduced there. The potassium ions are flowing out of that salt bridge to make up for the loss of the positive charges when those tin ions are reduced. So it allows us to complete the circuit, and it helps us keep electrically neutral solutions that each of our half cells are in. And last but not least, now that we've completed our entire circuit, this electrical energy could be used and our light bulb would turn on. We would see that light bulb on the top actually fire up and turn on. Now, if you can imagine, drawing out a galvanic cell the longhand way like we just did every single time would be really time consuming and really tedious, and we just don't want to do that. So there is a shorthand method to represent a galvanic cell, and it's very specific about what goes where and what represents what. In some of the previous pictures, because we were looking at the full picture, I put the anode or the cathode on either side, and we had to kind of figure out what was going on based upon oxidation and reduction. But when you are using this shorthand method, you have to be very specific. So the anode half cell is always on the left. The cathode half cell is always on the right. There's two lines that are written between them that represent that salt bridge. So that's the boundary, the phase boundary essentially between our anode and our cathode. So how we would read this here then is we have our solid zinc, and that's separated by a line right here. So solid zinc would be our electrode. That first line represents the phase boundary between our electrode and our aqueous zinc ions that would be in that solution. And that would be the reaction that would be taking place at our anode, where oxidation would be occurring. So solid zinc would be going to zinc 2 plus. And then on our cathode side, now we have our copper 2 plus ions that are in solution. And we have another line right here, which represents the phase boundary between our solution and our solid copper electrode. And at our cathode, that's where reduction is taking place. So our copper 2 plus ions are being reduced to solid copper. And so we know by looking at this shorthand notation that electrons always go from the anode, where they're produced, to the cathode, where they're used up. So we know electrons are flowing from left to right when looking at this shorthand notation. So it's important to include all of the parts, to include the phase boundary lines between our electrode and our solution ions, the double lines, which represent that salt bridge that shows our separation between anode half cell and cathode half cell, and then our other phase boundary on the right-hand side as well. So looking at this is essentially a really quick, short way to write out the really large images that we were drawing on previous slides. Now let's practice using this new shorthand notation to represent our galvanic cells. In our first example, we have solid copper plus 2 silver ions forming copper 2 plus ions plus 2 silver, which is solid. So we can see that copper is being oxidized, going from solid copper to copper 2 plus, and we can see that silver is being reduced. We have silver ions, and then we have elemental silver with no charge. So it's important to first identify what is your oxidation and what is your reduction half reaction. So for our copper, change my color here. For our copper, this is representing our oxidation reaction. And for our silver, that's representing our reduction reaction. And when we're using that shorthand notation, it's important that we have our anode on the left-hand side, separated by a salt bridge, and then our cathode on the right-hand side. And so our anode is where oxidation occurs, and our cathode is where reduction occurs. So once we have those definitions down, now we can use this information to quickly write out our galvanic cell. So we have our oxidation reaction, which would occur at our anode. We have our solid copper electrode separated by a phase boundary with our electrolyte solution, which is our aqueous copper ions. Then we have a double salt bridge separating our cathode, which is where our reduction is taking place, and we're going to have our electrolyte at our cathode, which is going to be our silver ions, and those are going to be separated by a phase boundary for our silver electrode, which is the solid. So right here, looking at that, if you see that, you also want to be able to interpret it the other way around. You want to be able to take a reaction and write the shorthand notation for the galvanic cell, but also looking at the shorthand notation, when you see this, you want to think, okay, this side right here, this is going to be our anode, and our anode is where oxidation occurs, salt bridge, and then separated by our cathode, and our cathode is where reduction occurs. So it's a very standardized way of writing a battery quickly. Okay, so let's try it for our next example as well. So we have iron, solid, being oxidized to iron 2+, so that's our oxidation half reaction. And then we have tin 2+, being reduced to elemental tin, so that would represent our reduction half reaction. So our anode is where our oxidation is occurring, so that's going to be with the iron. So we're going to start out with solid iron separated by a phase boundary from our iron 2+ electrolyte, the aqueous solution. Double lines for our salt bridge, and then moving on to our other cathode half cell, which is where reduction is taking place. We have our tin 2+ ions separated phase boundary from our solid tin. And just to label everything right here on our left-hand side, we have our anode, oxidation, our right-hand side, cathode, which is where reduction is taking place.